All right, welcome everybody. So I am in a little bit different. My camera is not working, so I'm just using my uh, laptop little cam. Let me just check one more time, make sure. Yeah, I don't know. It's not pulling up. So either way, so that's the way I'm going to run with this little live stream. And what I'd like to do is just kind of go with you guys, kind of explain a little bit as far as working on some rational functions. So this is a quiz that I gave my students that we did on rational expressions. So what I'd like to do is just kind of work through the problems and just kind of explain to you, step by step how I would be solving them. Now, I'm usually used to my camera being right here as I'm doing my work, so I'll try to kind of work back and forth. So it's a little bit different than what I am used to, but what I'm going to do is I'm going to plan on going through all this material. And if you have any questions, please make sure you to add them in on the chat. And once I am done going through the kind of quiz and going through the examples, I'll be more than happy to answer any questions you're working on in this class. Or if you have any questions on the material that I am covering in here, I'll be happy to cover that too. So, hey, Sigma, happy to have you join along. And Regal, hey, bud, how are you? I'm back over. So here's the quiz and at least going over the answers. So what you'll know is once I obviously next class period, when we go over this material, I'm not going to go in depth. I'll basically just say, hey guys, here's the work that we were going into. So, all right, let's go ahead and get right into it. I think I'll use blue, kind of sounds good for today, as it is a Friday and I want to kind of get over this as soon as I can. So, or at least try to go through this because, I think I gave my students like about an hour to complete this. And I know just with explaining, me working through the steps and explaining it, it's going to take a little bit. So GHP, hey, how are you doing, man? I'm glad you could join. So I will take a couple breaks here because obviously talking for this long, going over the break, I'll probably need some. So if you guys do have some questions, make sure you do ask them in the chat and I'll kind of work my way back through and try to answer them the best I can. All right, so let's kind of work through this first expression. Now, so the main thing is, when we're looking into these simplifying expressions, we see the word simplify. And basically what we want to try to do is when we're looking into simplifying, we're going to want to try to see if we can factor them or apply the operation. So you see in these two, we have subtracting, dividing, and this one has subtracting and dividing, which we call a complex fraction. But this one's pretty basic. It's just, we have a function in the numerator and a function in the denominator. And basically to simplify, what we want to do is say, can we rewrite this in terms of multiplication that we can apply the division property, basically meaning if we have the same term in the numerator and the denominator, that they're going to go ahead and divide out. So in this one, basically I'm looking for, it's a trinomial. So I want to see what two numbers multiply to give me -3, add to give me -2. And I can figure that out to be x minus 3. Actually, let's just write it down below. I think I have room. X minus 3 and then times x plus 1. All right. Now, this denominator one, this one can sometimes be tricky with a lot of students. But just remember, we could rewrite this as that is the same thing as -x squared plus 1. And what's important about that is we don't really like, when I'm factoring, I don't really like the negative to be with that square term. So I could also factor that out. I'm just going to write this kind of like above to save my work. I could factor out that negative to give me a x squared minus 1. And that's important because I recognize this as a difference of two squares. So a lot of students that I saw when I graded their work, they didn't rewrite this. They tried to factor this back out. And you could do it that way and then factor out a -1. That's fine as well. But a lot of students don't recognize the patterns as well to do it that way. So if you just think about factoring out the negative, then you can realize, or then you can see that this is a difference of two squares. And now what we can do is we can go ahead and apply the division property. See that both of these factors now are separated by multiplication. Hey, Oscar, how are you doing? Thank you. Well, not a professor, but I'll take whatever name you want to call me. But since they're multiplied by multiplication, now what we can do is divide them out. So the x plus 1 divided by x plus 1 is really just going to give you as, 1 over 1. So therefore, that's leaving me with a final answer of x minus 3 over. Now, you could leave this as is. You could write the negative up top. You could write the negative up on the bottom, or you could leave it right in front. Doesn't really matter either way. If you put the negative up top, the bottom. Obviously, in multiple choice, you'd want to check both the variations to kind of see what they might do with it. But there's a couple things that are important here. So now what we realize is that, we look at this, to find the discontinuities, we basically want, of a rational function, we want to see when can the denominator not equal 0. So, and this one is pretty easy. We can see that x cannot equal 1. Because when x equals 1, you're going to have, it's obviously going to be 0 in the denominator, so it's undefined. And since that is technically not removable, we would call that a asymptote. And I'm just going to use ASY as my asymptote. But however, 1 is not the only number that x cannot equal, because if we go back to the original problem, the original discontinuity is -1 doesn't work as well, because -1 squared is 1, 1 minus 1 is there. But what happened with -1 being is it got removed, it got divided out. So we call that a removable discontinuity, and a removable discontinuity is a whole. Okay, so 1 and negative, when you're identifying the discontinuities, you're not identifying just from the simplified version, but from the original equation. So basically, we're looking for what are the values that are going to make the denominator equal to 0. Now, in this case, we could identify these discontinuities right off the bat. And we notice that we want to check to see if they could be removable. We can see, though, from right off the bat, I know that x cannot equal 0. Because if x equals 0, then this fraction would be 0 in the denominator, so it would be undefined. And we could say x cannot equal -3 over here, because if x equaled -3, then obviously this rational expression would be undefined. So there I have my two discontinuities. I'm going to label them in a second, but let's go ahead and combine them and kind of see if there's anything if there's any holes that exist. So to get to add or subtract, remember we got to get common denominators. So we got to find the common denominator of x and x plus 3. And the common denominator of x and x plus 3 is just going to be the product of those two. Just like the LCD of 3 and 4 is 12, which is the product. So therefore what I'm going to do is I'm going to multiply my numerator and denominator, or my left fraction, by x plus 3, and my denominator by x plus 3. And then over here, on this fraction, I'm going to multiply by x over x. All right, so when I do that, I get x plus 3 over x times x plus 3 minus 7x over x times x plus 3. Now, I didn't insert the parentheses over here, but just remember when you're multiplying an expression times a variable, you're going to want to multiply both of those terms, okay? And then you can see that now they have the same common denominator, so I can combine the numerator. So therefore I have x minus 6x, or 7x, which is a negative 6x, plus 3, all over my common denominator, x times x plus 3. And then again, we're looking in to see if there's any holes, and we can't say these x's do not divide out, and that's why I wanted to kind of get to this step. These x's do not divide out because these are separated by addition. The negative 6x and the 3, those are separated by addition. Whereas over here, our quantities were separated by multiplication. So you can apply the division property across multiplication, not addition. So therefore, both of these discontinuities are asymptotes. Okay. So the next one is is division of rational expression. You can see this looks pretty kind of nasty, right? So the best way I would like to do this is let's just factor everything first. Let's try to simplify each one of these. So this looks like a difference of 2 squares, so x squared minus 4. So I'm just going to do x minus 2 times x plus 2, because at this point in the teaching, factoring is something that I've stressed very much. So I would expect my students to be able to quickly factor trinomials and binomials by special products. For the x squared plus 5x plus 6, I can see, let's see, that's going to be x plus 3 times x plus 2. Again, those are the two terms that multiply to give you 6, add to give you 5. Over here, this looks like a perfect square trinomial. So this would be x plus 2 times x plus 2. And now I'm going to write that in an expanded form, and I'll show you why in a second, even though that's also could be written as x plus 2 squared. But I'm going to leave that in expanded form just so we can see that better. And then again, here I have a difference of 2 squares, which would be x plus 3 times x minus 3. Okay, and if you guys need factoring practice, obviously I have tons of videos, and there's a lot of other tutorials that help you with factoring. But that's one thing that gets a lot of students with rational expressions is the factoring. But again, that is a prerequisite skill up to this point. So the main important thing is to remember when dividing rational expressions, if I was going to say, 5 divided by 1/4, well, that is the same thing as 5 multiplied by 4. So dividing by a fraction is the same thing as multiplying by its reciprocal. So basically what I'm going to want to do is rewrite this. Now, before I even rewrite this, though, I notice in these expressions, these x plus 2's divide out. Now, notice everything's separated by multiplication, right? So I can apply this multiplication property. So therefore, those two divide out, and I haven't even done anything yet. And therefore, also, let's see, nothing divides out over here. Okay, so now I'm left with x minus 2 divided by x plus 3. I'll just keep them in parentheses. Times, now I'm going to reciprocate this into x plus 3 times x minus 3 all over x plus 2 times x plus 2. Okay, so now let's go and look at what happens here. So did I have, yeah, okay, that comes in. So what I see here is the only thing else that divides out is my x plus 3's divide out. And I'm left with the x plus 2. Now, even though these both have the same variables and numbers, hey, AZ, hey, Jane Air, thank you guys for joining in. They don't divide out. They're not exactly the same, so we can't divide them out. So therefore, my final expression is going to be x minus 2 times x minus 3. Now, you could multiply these out, but, it really kind of depends on what is your, requirement for your teacher or for the test. I usually like to save time and just say, just leave them in expanded form. And then this is going to be x plus 2. We can just rewrite that as squared. Now, I wanted to leave this out just in case I wanted to see if I could divide one out because, it's important if you have, if one divide out, I just wanted to remember that there's still one there because it was x plus 2 squared. So now let's go and talk about the discontinuities. So remember, when we're looking at our discontinuities, here is we're looking at what our original function here, where the x plus 3 divided by the x plus 2. But what we noticed was our x plus 2's got divided out, as well as our x plus 3 is also got divided out. So we're going to have wholes. So I'm just going to say wholes at x equals negative 2 and x equals negative 3. And then we look at what's still left in the denominator. That's still a discontinuity. So my only discontinuities could be at negative 3, 3, and therefore I can say my asymptote divided by that function. My asymptote is going to be at x equals negative 2. No, sorry. What did I have in there? I'm sorry, I don't have my work. Let me work in this. So x equals negative 2. Oh, x equals positive. No. Yeah, that's just a whole. So it's obviously there's a whole, but that's going to be my asymptote. So that's not going to be my whole. Sorry about that. Let me erase that. I wasn't looking at my thing. So my x minus 2's got divided out, which is removable, but you can also see that it's still there. So therefore, it's going to be my asymptote. So this is my only whole is going to be at x equals negative 3. And then my asymptote is going to be at x equals negative 2. Okay. And yeah, there you go. Oh, thank you very much. All right, let's go ahead and work on D here. When looking at this one, this is a complex fraction again. Again, I see this x squared minus 4x plus 3. I'm going to want to simplify this. So I'm going to want to factor that out into, let's see, let's write this, that'd be x minus 3 times x minus 1. Okay. And now when I'm multiplying that, you see that my other two denominators are x minus 3 and x minus 1. So if I want to get rid of all the denominators, all I got to do is multiply everything by this same LCD. So what I can do is if I multiply everything by x minus 3, x minus 1, that's going to give me, let's show this. So let's rewrite this as over 1. So if I rewrite this in factored form like that, now if I multiply everything by my LCD, which would be x minus 3 times x minus 1, then the x minus 3's would divide out, if here I multiply by x minus 3 times x minus 1, my x minus 1s would divide out. And then over here, if I multiply the x minus 3 times x minus 1, these would go ahead and divide out, both divide out. So therefore, I'm left with, now this is where it kind of gets a little tricky and a little confusing because there's so many things going on, and I can even see like my work, it's like kind of crazy. But what you can see, what's left over is just a 1. And then over here, I have the negative 2 times x minus 1. So it's going to be negative 2 times x minus 1. And then my denominator, I'm just left with a 3 times x minus 3. Okay, now I can go ahead and simplify this a little bit further. I could leave it like this, actually, and actually let's just save some time and let's just leave it in that format. Nothing else is going to divide even when you distribute that through. But let's go and look at our discontinuity. So we had two discontinuities in our denominator. We had x equals 1 and x equals 3. So x cannot equal 1 and x cannot equal 3. But what we noticed here is my only denominator that is going to be left through, or the only one that got that is still in the simplified version, is going to be x cannot equal 3, which would be your discontinuity. So at well, I kind of realized a couple ways that we write this. Yes, x cannot equal 1, but we could say our asymptote is when x equals 1, and our whole is when x equals negative 1. But yes, those are like your discontinuities. Which I kind of didn't really, technically we want to say like x cannot equal 0, so our asymptote, I'll just write it over here, x equals 0 and negative 3, those are where the asymptotes occur. But I don't know whether, so those are where the asymptotes, now they are discontinuities, they are not defined for our domain, but that is exactly where those occur. And okay, so then over here, I don't know why I'm writing them like that. I guess it's just going crazy. So let's go back to our pen here. If I want to go ahead and write the discontinuities here, I know that my two discontinuities is, x cannot equal 1 and x cannot equal 3, because those are two values that make our denominator equal to 0. Now, 1 got removed from our simplified version. 1 is no longer there, so I can say x equals 1 is a whole, and x equals positive 3 is my asymptote. Okay, so basically you want to identify all of your discontinuities, and then once you've identified your discontinuities, then what you want to do is see if it's in the simplified version, and if it's still in the simplified version, then obviously it remained as an asymptote. If it gets divided or simplified out, we can look at it in terms of a whole. X equals negative 3, my whole. I was trying to look at this example. Allie completing the square. I will get to that. Let me just go ahead and take a quick little break. Kind of see if there's any questions. Hey, Janator, Allie. How are you guys doing? I'm glad you guys could kind of join me today. I'm just going to finish up this. I do have some completing the square stuff that I came into. Alex says, just came by to say thank you. Take Algebra 2 and Pre-Calculus Sophomore, and you've done help me out. Well, I'm very happy to help you out, Alex. I do appreciate you joining in and saying hello, and then just offering a quick little thanks. I just feel like there's much information that I can possibly, provide to you guys. Hey, Christopher, that, I feel like that's, whatever I can help, whatever I can do to kind of help you guys out, with your math and kind of go through things. So appreciate you guys come joining in. There is one other problem though I did forget. I think I'm looking back at this problem and I'm seeing that the discontinuities originally, which I didn't label, which is like a good idea to do real quick, is when you look at this, we know our discontinuities, x cannot equal negative 3, x cannot equal negative 2, x cannot equal negative 3, and x cannot equal 3, right? If you look at just your denominators of your whole expression, those are all your discontinuities. Well, what's only thing is left over is x equals negative 2. So therefore, my whole is going to be at x equals negative 3 because that got divided out. And then at x equals No. Well, let me look at that. I'm going to come back to that. Go back to that point. Because I want to think. I'll come back to the explanation here. Alias, I'm doing England. I'm so squared. I'm going to watch your video so I won't fail. So say I will get to, well, Himashu, make trig. I have tons of trigonometric functions. We just kind of already finished up on trig though. So this was actually a little bit rational functions. It's something that we talked about a while back ago. And that is, but so it's something we've already kind of covered as far as in our trig, but we will be, we're kind of wrapping up as far as trig, but I will be probably having some videos on trig, just as far as we prepare for our end of course exam. And I am from Jacksonville, Florida. Go ahead and turn it to the bottom bin. All right, let's go ahead and knock out the asymptotes, the intercepts of each equation, so we can kind of wrap this up. So the first thing, it just says identify all the asymptotes. That means vertical, horizontal, and slant asymptotes. And then identify the x and the y intercepts. All right, so in this example here, we have x squared minus 3x minus 1. Same thing as multiplying by it's simple. Yeah, okay. So that is not going to be my discontinuity. I'm just going to erase the a because discontinuity, yeah, that's fine. Because that's the same thing, dividing is the same thing as multiplying by its reciprocal, and therefore my -2, and then my -2, and my +2. Oh, +2, yeah, because that happens double squared. Okay, yeah, we're good. We're good with this one. Okay. I had to just go back. I had a brain freeze kind of thing. All right, so let's go back and let's go and take a look at horizontal asymptotes. So the first thing I like to do as far as finding these is let's go ahead and find the vertical asymptotes. So the vertical asymptotes is when the denominator is equal to 0. And we don't really need to do too much math here, guys. You know, x plus 7 is equal to 0 when x equals -7. So we can say the vertical asymptote occurs at x equals -7. Now, you do want to be careful of any kind of holes, but I'm not going to factor this, you know, right now, and I'll get to the factoring here in just a second. But even without factoring, I can identify, or this isn't even factorable. So I know that x plus 7 is not a factor of that problem. The next thing I want to do is look at the horizontal asymptote, but this does not have a horizontal asymptote because the degree in the denominator is smaller than the degree in the numerator. So it says identify the asymptotes. The horizontal asymptote is not an asymptote. So therefore, I'm just going to get right into the slant asymptote. So to find the slant asymptote, all I'm simply going to do is take the divisor and divide it into my numerator. 3x minus 1. So x divides into x squared. X times x is x squared. X times 7 is 7x. Okay, then I group and I will subtract. X squared minus x squared is 0. Then negative 3x minus 7x is going to be a negative 10x. X divides into negative 10x, negative 10 times. Now remember, when you're doing your slant asymptote, it's y equals the quotient. And once I do this, I realize, though, once I'm subtracting this is going to be done, well, I guess I'll just show my work. Negative 10 times x is a negative 10x. Negative 10 times 7 is a negative 70. And you can bring down that negative 1. Okay. Now what happens is when I subtract these rows, I get a 0 again, and then I get a positive 69. Now, x does not go into positive 69, so that's your remainder. But again, for the slant asymptote, we don't really care about the remainder. As we approach infinity, it ends up going into 0, so it's like does not affect my asymptote. So my slant asymptote is just going to be y equals x minus 10. Okay? So therefore, I have a slant asymptote. Now, the next thing I want to do is go ahead and find the x-intercept. And I think that's the one where, man, yeah, I was really good with you guys. I gave you another one. Since this is non-factorable, right, there's no two numbers that multiply to give you -1 and add to give you -3. I was kind of mean to my students. I made them do the quadratic formula again. So, again, if you want to find the x-intercept is when y is equal to 0. So if you replace 0 with y, and then to solve that, you can basically just set the numerator equal to 0. Well, the problem, I'm going to do this in a different color just because I know it's going to be close. This is non-factorable, right? So you set the numerator equal to 0, because if this is equal to 0, you multiply by x minus 7 on both sides, so you have 0 equals numerator. So you're going to have to use the quadratic formula. So the quadratic formula, again, x equals opposite of b, which would be 3, plus or minus. Okay. There you go. You too, bud. Have a good weekend. Plus or minus the square root of b squared, which is negative 3 squared, minus 4 times a, which is 1, times c, which is negative 1. Okay, and let's just kind of do a little math in our head to kind of speed this up. So negative 3 squared is going to be 9. Negative 4 times 1 is negative 1. Negative 4 times negative 1 is positive 4. So 9 plus 4 is 13. Oops, I'm sorry. I forgot to write this. That's all over 2 times a, which in this case is 1. All right, so, man, I don't know why I went that sideways. So the x-intercepts, which is this work all under here. So the x-intercept, let's try to finish this up, is going to be 3 plus or minus the square root of 13 over 2. And we can write that as coordinate points, or, you know, just for the sake of my space, I'm going to leave that as my 2x values, okay? All right, and for those of you that are kind of joining in, I'm almost about halfway done through my test. I'm going to continue here working, finishing up, and then what I'll do is I'll go back and answer any questions that you guys may have. So if you do have some questions or something I can help you out, or anything that I covered in this problem, you know, please let me know, and I'll be more than happy to discuss them or kind of get them after I'm done. But we are right at the halfway point. To find the y-intercept, basically, if you guys think of like the y-intercept, that's basically where the graph crosses the x-axis. So that's going to mean x is equal to 0. So just think about if I set x equal to 0 for all of these values, I'm just going to be left with negative 1 over 7. So y equals negative 1 over 7. All right, so that's about as, so you just replace 0, 0, 0, negative 1 over 7, good to go. All right, so the next one is vertical asymptotes. So let's go down to the next one. Again, let's find the vertical asymptotes first. Let's go back to blue. So vertical asymptote is, now this one might not be as straightforward. This one's pretty easy when you set equal to 0 to solve for x. But here, if you set this equal to 0, x squared plus 5 equals 0, x squared equals negative 5. Well, next operation is going to be to take the square root, and I can't take the square root of a negative number and get a real value. So therefore, it's going to be like imaginary asymptotes, which obviously are not going to exist in the real number system. So therefore, there are no vertical asymptotes. So I am just not going to apply my vertical asymptotes. So then let's move on to the horizontal asymptotes. So the horizontal asymptotes, again, guys, is a comparison of the degrees in the numerator and the denominator, or the degree, which is the highest power. And what you can see here is the degree in the numerator is smaller than the degree in the denominator. So therefore, by the horizontal asymptote test, the horizontal asymptote is going to be at y equals 0. All right. Then the next one is to find so that's all the asymptotes. There's just one horizontal asymptote. There's no vertical, then there's no slant. To find the x-intercept, again, I didn't show it because I knew that first one was a lot of work. X-intercept is when y equals 0. So let's actually work this one out so you can see why I quickly just set the numerator equal to 0. If I set y equal to 0, then I have x plus 1 over x squared plus 5. So if I need to solve for x, I got to get that off the denominator. So if I multiply by an x squared plus 5 on both sides, what you'll notice is that goes to 0. And those divide out, so I'm just left with x plus 1. That's why the shortcut for, don't know why that looks so bad. That's why the shortcut for finding the x-intercept of a rational expression, you can just set the numerator equal to 1. So therefore, we can see that the x-intercept is x equals negative 1. And then to find the y-intercept, I'll kind of show my work again with this one. Let's use purple. For the y-intercept, I'm just going to set x equal to 0. So let's actually just plug this one in. Y equals 0 plus 1. And that's basically what I was saying here. I was just saying 0, 0. Plug 0 in for 1, and then you'd have 0 squared plus 5. Well, that's just going to give you y equals 1/5. Okay? More factoring. Dang it. All right, so on the next example, we see there's a little bit of work here. Now, again, this kind of looks confusing because, again, we have to factor, and that's basically one of the hardest parts about the rational expressions is doing all of the work here. All right, so first thing I'm going to do, let's factor out the numerator. When I factor out the numerator, you can see I can factor out a 3. By factoring out a 3, I'm left with a x squared minus 1. That's kind of interesting. We'll get to that in a second. Over here, I want to see what two numbers. Now, this is a trinomial, so I'm not going to do any long work. I'm going to say, all right, so trinomial, that means I could factor in a trinomial can break it down into two binomials. So let's say my first two is going to be 2x and x, because 2x times x gives me 2x squared. Well, what two numbers multiply to give me 1? Well, that's positive 1 and positive 1, or negative 1 and negative 1, right? But if I want my middle terms to add up to be negative, that means I want my two terms to be negative 1 and negative 1, right? So that it becomes my factored form. And, we can double check our work. 2x times x is 2x squared. Negative 1 times negative 1 is positive 1. 2x times negative 1 is negative 2x. X times negative 1 is negative x. Negative x plus negative 2x is negative 3x. So that works. Now, I can continue this a little bit further because I see this x squared minus 1. We already factored that out. I can continue factoring that one more time. So let's go ahead and do that because something interesting happens here. X minus 1 times x plus 1. And then I have 2x minus 1 times x minus 1. And what happens here is the x plus x minus 1s, they divide out. That means that x equals 1 is a discontinuity and it is a whole. Now, I'm going to need that information here in just a little bit. All right. So let's go ahead and finish the rest of the problem and, let's kind of identify what's going on. So the nice thing about factoring everything is when I want to find the vertical asymptotes, remember vertical asymptotes are just setting the denominator equal to 0. Well, now that I've already done the work of factoring, I can just set the factored form 2x minus 1 and then times x minus 1 equal to 0, and I can just apply the zero product property, set each factor equal to 0, and then solve. Save a little time. I'm just going to have x equals 1/2 and x equals 1. Now, those are going to be your vertical asymptotes. Yeah, my vertical asymptotes. Okay. Oh, but I'm sorry, that's not my vertical, that's my discontinuity, but x equals 1 is a whole. There you go. So that's not going to be an asymptote. It's just going to be x equals 1/2 because that actually got divided out once I simplified. All right. For horizontal asymptotes, I need to apply the horizontal asymptote test, which is, again, comparing the degrees. You notice that the degrees here are the same in the numerator and the denominator. And when they're the same in the numerator and denominator, you're going to take y equals the ratio of the leading coefficient over the leading coefficient. So y is going to equal 3/2, okay? And that's it. Horizontal asymptote is when they are the same degree, it's just a ratio of the leading coefficient over leading coefficient. To find the x-intercept, again, I'm just going to set y equals 0 or set the numerator equal to 0. So I have 3x squared, kind of running out of space here. 3x squared minus 3 equals 0. Now, if I add 3 and divide by 3, I get x squared equals 1. And then when I take the square root of both sides, I get x equals plus or minus 1. Now, this is important because we already know that there's a hole at 1. So a graph cannot cross the x-intercept at a hole. So the only x-intercept, we'll do this in like another color, the only x-intercept occurs at x equals -1. Even though we saw the solving it gave us positive 1, that's a hole, so it's not actually an x-intercept. And then to find the y-intercept, all I'm simply going to do here is just go ahead and plug 0 in for x. That goes to 0, 0 in for x, 0, 0 in for x, 0. And then I'm just left with -3/1. All right, so next one is going to get into solving. But before I do that, I'm just going to take a little break and just kind of come over to you guys and just kind of see if you have any other questions. Where you're at. So let's say I left. Yes, hey, Ellie. Yes, I am teaching in my classroom. My webcam is not working right now, so that's why I'm using my kind of built-in webcam on my Mac. So I'm not sure how it looks or sounds or anything like that. But I wanted to do this live stream today, so I just had to go with what I had. So yes, this is the back of my classroom. I'm sitting at my a desk. Shady says, my class is currently working on Bezout theorem, quite a quickie lesson. I do not recall that theorem or going back through it. I don't remember it. Maybe my earlier days or in college if I went over it. I just don't recall though. But currently right now I'm just teaching pre-calculus and calculus. So that's kind of where we're at. He says, how's your day going? It's going pretty good. You know, usually at Fridays I'm like really, really exhausted. And I was kind of worried about doing live stream on Fridays or even like saying I'll do one. But I'm not sure if it's just I made the decision today saying like, hey, I'm going to do a live stream. And then that kind of kept my like enthusiasm going throughout the day. But I will say I'm not as tired as I usually am. And I think that might have been like at lunch, I'm like, I'm doing a live stream. So I scheduled my live stream. And I'm very happy that my videos have helped you so much. It is a joy for me to, hear from all of you that, have maybe struggled in math like I did. And, I've been able to do well just with a little assistance. And I think that's the main thing that a lot of students, need to understand is, math is not something that you get or you don't get. It's not something you're good at or you're not good at. It's not something you turn off or you turn on. It's a process. And we all learn different ways and we all learn at different paces. And, as long as you continue working like a lot of you guys are coming in, and doing the work, and trying to learn, you'll see that progress. You'll see that you will start growing and you'll start making those connections because, the world of mathematics is such a complex topic that, your brain, it takes time to make all those connections and to really make sense. So don't be hard on yourself. I know a lot of people are really hard on themselves. Like, I just don't get it. It just doesn't make sense. It's like, give yourself time. Things will come through with a lot of practice and with patience. All right. So let's go and wrap this up so I can get my live stream over with and then I can go ahead and get home. So on solving rational equations, it's kind of the same thing. A lot of the thing that was important with all of this mess up here was identifying these discontinuities, because if we find a solution that ends up being a discontinuity, it's what we call an extraneous solution. So the same kind of thing of what we did here in number 2, as far as getting common denominators, I like that. And we could apply that process in solving rational equations if we want to. I could get common denominators and subtract these. I could get common denominators and add these. I could get common denominators and add these. You can do that, and there's nothing wrong with that, but there's even an easier method with using the LCD. And rather than trying to use fractions, like use fraction operations, we can just eliminate the fraction by multiplying by the least common denominator. So in this example here, I want to see what my least common denominator is of x plus 1, x plus 4, and x squared plus 5x plus 4. And what's nice about this is when I factor this one down, when I factor this trinomial, I get x squared plus, no, not x squared plus 4. I get x plus 4 and x plus 1. Okay. And now you can see that the common denominator of all of these, and a lot of times I like to write them up so I don't forget it, the LCD is, let's write it down below. My LCD here of all of these fractions is just x plus 4 times x plus 1. So now what I can do is multiply every single expression by the LCD. And what's really cool is when I do that, then I get rid of my fractions. I don't have any more fractions when I do this. So watch, x plus 4, I don't know what that was. So when I multiply by x plus 4 times x plus 1, and then here I do x plus 4 times x plus 1, and then I do x plus 4 times x plus 1. Okay. Again, my x pluses 1s divide out. My x plus 4s divide out. And then also, you can see that here, those are the same. X plus 4 divide out, x plus 1s divide out. So now I'm just left with 3 times x plus 4 and minus 2 times x plus 1 equals 1. And then now, guys, this is just an algebra 1, equation. We're just going to distribute, combine like terms, and then solve. So I get 3x plus 12, right? Applying the distributive property. Make sure you keep the negative here. So therefore, this is a negative 2x minus 2 equals 1. 3x and negative 2x is x. 12 minus 2 is going to be 10 equals 1. And then I say x equals negative 9 as I subtract a 10 from both sides. And then I just want to make sure, can x equals 9, is that going to make my denominator 0 for any of these? And it does not. So therefore, that is all good. I'm ready to move on to my next problem. So the next problem looks like it's the exact same kind of process. The only difference here is I have an x in one of these numerators. But again, I'm going to want to look to factor this, and I can see what two numbers multiply to give me positive 8, add to give me negative 6. Looks like negative 4 and negative 2, which is again, oh, that's the same as those two. That's kind of nice. All right, cool. So it's going to be x minus 4 times x minus 2. And that's kind of nice. So therefore, my LCD is going to be exactly the same. They all share the same LCD. I kind of like that. So therefore, in this case, again, I'm going to do the same thing because I really want you to see what is... Actually, you know what? We already saw what happens. So when I multiply the LCD times this, the x minus 2s is going to divide out, and I'm just going to be left with x minus 4. I'm trying to speed this up. If I multiply the LCD times here, in the numerator, the x minus 4s will divide out, and I'm left with a positive 1 times x minus 2. And then here, if I multiply the LCD by this expression, both numerator and denominator will divide out, but I'll be still left with 2. Okay, so now I gotta have to go ahead and multiply everything out. So I have x squared minus 4x plus x minus 2 equals 2. Combine, now I notice that this is a quadratic. So here, this is linear. I wanted to get them to the same side and combine them. But over here, I notice this is a quadratic. So we're solving a quadratic, and we're going to want to set it equal to 0 and see if I can solve or quadratic formula or factor and solve, which would be preferred. So, but I can only apply the factoring and zero product property if it's set equal to 0. So let's go ahead and subtract a 2 then on both sides. So now I'm left with x squared minus negative 4x plus x is going to be negative 3x, and then minus 4 equals 0. I can factor that into an x minus 4. X minus 4 times x plus 1 equals 0. And again, you can see the power of having everything set equal to 0. Now I can set them both equal to 0 and say x is equal to 4 and x is equal to negative 1. Those are the values that are going to, now I set them both equal to 0 and then solve. But the problem is when I plug in 4 back into my x, I see that 4 minus 4 is 0. That was going to make my denominator 0. So this is an extraneous solution. Okay, it's actually not a solution to the equation. All right, last but not least is this example. Now this one kind of tricky because it doesn't follow the same process as these two, right? So, but if I look at this as far as like numerator and denominator, I can see that my denominators are 1, 1, and x. So, well, my LCD is going to be, if I kind of like do the same thing as multiply everything by the LCD, I notice here that my LCD is now equal to x. So why don't I just multiply everything times x? Because that's what I did in the other example, and that worked out okay. So when I multiply everything by x, I get x squared. 1 times x is x, and then 6 times x equals 6x. Well, that's perfect. I don't have any more fractions. That's awesome. But now what I need to do to go ahead and solve is I just need to set this equal to 0 and then you factor and solve or quadratic formula. So I have x squared plus, if I subtract 6x, so that's not going to be plus, that's going to be a minus. So I subtract, so that's going to be minus 5x equals 0. Okay, well, this isn't a trinomial, but I can factor out an x. That's going to be left with an x minus 5 equals 0. Now, I didn't show the zero product property here, but you can set x equal to 0, and then x minus 5 equal to 0. That's a really long minus 5. So therefore, that equals x equals 5. Now, again, we want to go back and check our solutions, make sure they don't make us extraneous. This isn't right. What did I do? Oh, the x is divided out. I was wondering, I'm like, I did some kind of mistake. You're right. These x's here, these divide out, right? So I made all mistakes. Saturday still school. All right, so yeah, I made a mistake. So that X is not there. All wrong. Sorry about that. I was like, I don't remember doing that answer on my answer key. Okay. Now I get this. Now let's set this equal to 0, subtract a 6. So I get x squared plus x minus 6 equals 0. Now I can factor this into x plus 3 times x minus 2. Again, the reason why that works is because 3 times negative 2 gives me negative 6. 3 plus negative 2 gives me a positive 1. Now I can use the zero product property. And therefore, x equals negative 3 and x equals 2. Done. Now, again, we want to go back and check our answer to make sure that they work. And obviously, the only discontinuity here is at 0. And neither of these are at 0. So therefore, we are done. So there you go, ladies and gentlemen. That was the quiz. If you're dealing with anything, a review for rational expressions, simplifying, asymptotes, intercepts, solving, hopefully this helped you out. Does anybody else have any other question? I'm just going to kind of go back and see if I make sure I didn't miss anything from, ooh, that's kind of weird. Okay, there you go. All right, so the villain, happy to help you out. Math's so fun when you have to solve the equation because it makes you feel like a boss. Jeez. All right, Takari, you're a wizard. I have just done a lot of practice, Takari, just a lot of practice. I mean, think about I tell my students, like, think about my life. Like, I do math problems. Like, I'm not even a mathematician. I mean, I have a math degree, but I'm like, I do a lot of math problems, right? A lot of math problems, during the day. And, so that helps you do a lot of practice. Obviously, if you do something every single day over and over. Now, again, I'm still going to make mistakes. Like, for instance, I had like a brain fart here on C. Like, I was just having confusion. Like, again, when we look at our discontinuities, we want to look at the discontinuities from, what it represents. But like, I'm going to have brain farts just like everybody else, thinking through things. So, it's just, it is what it is, kind of comes through, and, we just got to work through them and, practice. I mean, that's where a lot of things kind of come from. So, all right, well, I'm not seeing if I missed any other questions by anybody, but I will plan on going live hopefully next Wednesday as well as next Friday. So I'll be happy to answer any questions if you guys have anything, if you want to prepare for those live streams, and I'll make sure I put a note, and then you can go ahead and add in from that, and I'll be happy to help you guys out. I think it's called the rational root test in the U.S. determining rational zeros. Oh, okay. Well, Anna, have you helped so much with the passing test? You explained very well. Well, thank you very much, Anna. I'm very happy to help you out. All right. Yeah, the rational zero test. I can do something really quick on the rational zero test. Well, I don't really have much time, but I can go through. I mean, basically, the rational zero test is, when you have a polynomial, okay, let's just say x to the n, let's call that p, dot, 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 and q. Now, the fundamental theorem of algebra is saying that this graph is going to have the number of x-intercept is equals to its degree, right? So, but again, the number of zeros. But we got to be careful because, like, we could cross at like 1 and 2, like that's great. Or 1/2, like these are all rational numbers. But that doesn't mean like where all of our graph is always going to cross. Like the graph, like this zeros can sometimes be imaginary zeros, or sometimes they could cross at like the square root of 5, which is a irrational. It can still be a 0, but it's irrational. So the rational root test is what just allows us to find the rational zeros. Now, the reason why that's helpful is because if I know what the rational zeros are, then what I can do is I can use synthetic division to further divide my polynomial until I get to either a cubic or a quadratic that I can apply, preferably like the quadratic formula to then identify my either irrational or imaginary roots, because otherwise you're not going to know where the imaginary roots are, right? Or the irrational roots. So if we can identify the rational zeros and then test them using synthetic division, then we're all good. Now, just to remember, so the basic idea of this is the rational zeros. When you have a function, and I'll do like an example, y equals, 2x, I don't know, cubed, ... doesn't even matter what everything else is, plus 7. All the rational zeros is plus or minus the factors of, P over Q. I don't know. Why did I write that PQ? I guess I was saying PQ, but that's actually the other way around. This is represent our P over Q. Is the rational zeros of our factors of P, which in this case would be 7, over plus or minus our factors of Q, which in this case would be 2. So then what you basically all just go and do is just take out the factors of 7. Well, the factors of 7 plus or minus are going to be 7 and 1. Now, I chose something relatively simple here for you. Obviously, you could have numbers that have a lot of factors, over plus or minus the factors of 2, which are 2 and 1. And then we just list them all out. So basically the list of rational zeros is equal to, plus or minus 7 plus or minus 7 over 1, plus or minus 7 over 2. Now you could write the plus or minus just in front and then write all those out. That's usually what I like to do, but in this case I already started, so I'm just going to go over this. And then you could do plus or minus 1/2, comma, plus or minus 1 over 1, which is really just 1, right? But I'll just write out. So again, what we could do with this information is these are all the possible rational zeros. Now what you need to do is test them. So by finding each rational zero, what you would do is just, use synthetic division to test with whatever your polynomial was for each of these zeros. And if you get a remainder 0, then you're good. And what you can do is you can take your quotient now and then try to further solve that down to get to identify your irrational or imaginary, if that's the case that you have. All right, that's an in. So Gabe says, can you do some videos on applying the properties of logarithms? Yes, I can. I can let you know when my playlist, I'll go ahead and send a comment on the playlist that I can definitely let you know of, my videos. We unfortunately don't teach the logarithms anymore, as much of my class so we don't go over it. I do kind of teach it. I did have some new videos in calculus. We went over more of logarithms, but we don't really do much, anymore, but I do have a ton of video of logarithms. And actually, if you just search my channel, logs, Gabe, if you go ahead and search my channel or just search YouTube, but anyways, if you just type in #logs, and sometimes you might have to add in a McLogan, but if you type that in, you will see all my playlists on logarithms, and I have a ton of videos on logarithms. They're all organized in the playlist, so you can go and check those out. And then if you have some other questions, I'll be going live next Wednesday and Friday. Bring up those questions. I'll be more than happy to help you out with that. I wish I had your brain knowledge. No, you don't, villain. I wish my brain knowledge. Math, I struggle with math. I had just as much hard time with math as you did, or as a lot of you guys did. I just decided I want to be a math teacher and work through it. And I spent a lot of long hours in the library, a lot of long hours in the tutoring lab, learning what I was supposed to learn that I didn't understand when I was in high school. And it was a long journey, and it was a lot of stuff, but I've worked very hard and I've done a lot of math problems. So, it might make sense to me, or it might look easy for me, just like it looks easy for a professional, athlete doing anything they do. But, you kind of forget sometimes the hours and the amount of practice that people put into something to make something look easy, and there's a lot of things that, I do for the first time. It's like, oh, I'm never going to be good at this. But, then you just keep on doing it. You're like, oh, that's actually really easy, So, it's just kind of the evolution of, practicing and working things out. Well, thank you, Alte. I appreciate that. And the villain, well, hey, man, I'm going to be here for you all year long. And hopefully I've helped your grade and everything else. But all right, guys, I have been going live for just about an hour now, so I am going to sign off. Thank you very much, Woods. I appreciate you chatting in, and I'm happy that I was able to help you with your math this year. But I am going to say bye-bye for now, and I will check back with you guys next week. All right? So have a good weekend, everybody. I'll see you next